Geometric sequences. Sometimes they're called geometric progressions, or you may even see them written as GPs. A geometric sequence has a common ratio, denoted by the letter R, between consecutive terms. This means to get from one term to the next, we multiply by the common ratio. In this example, we're multiplying by 2 on each occasion. The common ratio R can be negative, could also be a fraction. Next, a geometric sequence converges if the common ratio is less than 1 but bigger than -1. So we can write that as the modulus of R is less than 1. And that's because if we continuously multiply by a number which lies between -1 and 1, the value will get smaller and smaller, tending towards 0. So in this example, we can see that we multiply from a half to a tenth, we multiply by a fifth. And we do that in each case. And that would be repeated indefinitely, or for as long as the sequence is defined. Next, we have an alternating sequence. This has terms which are alternatively positive and negative. In this case, we can see that it goes from 3 to -9, then from -9 to 27, and this gives us a multiplying factor. We multiply by -3. It is the multiplying by the negative which changes the sign. Finally, we can also have a periodic sequence. A periodic sequence cycles through a repeating sequence of terms. In this example, we can see the terms 1, 4, 2, then they are repeated, and this is repeated indefinitely. So we can say that this sequence has a period of 3. It should be noted that a periodic sequence can also be alternating. Next, the nth term formula. This is un is equal to ar to the power of n minus 1, where a is the first term and r is the common ratio. We can see this by thinking about a sequence which is first term a and a common ratio of r, so the second term is ar. The third term is ar squared. The fourth term is ar cubed, and you start to see that each term is one less on the power than it is the term. So we end up with un is equal to a times r n minus 1. Let's look at example 8. Here we are asked to find the 10th and the nth terms in the following geometric sequences. To find the 10th term, we could just find the ratio and keep multiplying. However, it is quite often easier to find the formula first. So, for part A, we can see the term is 3, then 6, then 12, and then 24, etc. To find the common ratio, we take a term and divide it by the preceding term. So we could take 6 and divide it by 3. And at this point we should note that had we taken 12 and divided by 6, or in fact 24 divided by 12, we would get the same common ratio, which is 2. So this is one way of checking if a sequence is geometric. We also know the first term is 3. So that means to find the 10th term for part 1. So 10th term, u10, meaning the 10th term, is equal to a, which is 3, times the common ratio, which is 2, times 10 minus 1, or to the power of 10 minus 1. So we end up with u10 equals 3 times 2 to the power of 9. Now 3 times 10 to the power of 9 times 3 is the same as 3 to the power of 10, and 3 to the power of 10 is 1536. We could use a calculator as well. What we'll notice here, we actually at the same time have found the nth term, because we know that the nth term is equal to the first term, which is 3, times the common ratio, which is 2, to the power of n minus 1. So we've found both. Next, let's look at part B. For part B, our ratio is 40, minus 20, 10, minus 5. So here we can see that the sequence is getting smaller and it's oscillating between positive and negative. Again, to find the common ratio, we take a term and divide it by its preceding term. So in this case, the common ratio is minus a half. Therefore, you may want to actually write down the formula first of all. So un is equal to the first term, which is 40, times the common ratio to the power of n minus 1. Being careful to keep the negative half inside the bracket, just being careful with our indices. Then, to do part 1, we want to find the 10th term. So this is going to be the first term times minus a half to the power of 10 minus 1, again 9. And here we can take our calculator, typing that in, and we get an answer of minus 5 over 64. Next, to look at example 9. Here we are told the second term is 4 and the fourth term is 8 of a geometric sequence. And we're also told that the common ratio is positive. And then we're asked to find the exact value of the 11th term. So let's start by writing what we know. We know that the second term is equal to 4. We also know that that is equal to a times r to the power of 1. We're also told that the fourth term is equal to 8, which is equal to ar cubed. And that's because the formula is equal to un equals ar to the n minus 1. So each time, probably worthwhile just writing that down. Okay, here we have a simultaneous equation. We could try and separate, but actually in this case it is easier to rewrite this and think, because the left hand side of one is equal to the right hand side of another, we could write this as ar cubed divided by ar is equal to 8 divided by 4. Then, cancelling, the a's cancel, r divides into the bottom once, and that becomes an r squared. So therefore, r squared is equal to 8 divided by 4 is 2. Square rooting both sides, we have 2. Now normally, we would have a plus or minus there. However, we have been told that the common ratio is positive. Therefore, we deduce that r is equal to the square root of 2. Well, if r equals the square root of 2, we can go back to our original equation, i.e. the u2 equals 4 equals ar1, and we could think that a times the square root of 2 is equal to 4. Which then means a is equal to 4 divided by the square root of 2. Which simplifies to 2 root 2. At this point we can now try and find our answer. So we're asked for the 11th term. So this is equal to 2 root 2 times the common ratio, which is root 2, to the power of 11 minus 1. So u to the 11 equals 2 root 2 times the square root of 2 to the power of 10. So u to the 11 is equal to 64 root 2. Now to example 10. Here we have a sequence 3, x, x plus 6, and we are told that it is geometric. And we're also told that all of the terms are positive. Now remember, in a geometric sequence, the common ratio is defined as one term divided by the preceding term. Well, that means that's the same as x plus 6 divided by x. So one term dividing by its preceding term. Now we have an algebraic fraction in an equation. So multiplying this out gives me x squared equals 3x plus 18. Rearranging, Next, we want to try and solve this. This factorises. Giving us that x is equal to 6 or x is equal to minus 3. However, we can see, that x must be positive. So therefore, x is equal to 6. So now we have found the possible value of x. Next we want to find the 10th term. So for b, the 10th term, we know now that the first term is 3, we know the second term is 6, and then we know that the third term is 12. So hopefully it is obvious to see that we are multiplying by 2 in each case, which means the common ratio is 2. So the 10th term is equal to the first term, which is 3, times the common ratio, which is 2, to the power of 10 minus 1. So multiplying this out, we get 1536. Example 11. What is the first term in the geometric progression 3, 6, 12, 24? Hopefully you can see here the common ratio is 2. And the first term is 3. So a equals 3 and r equals 2. Remember, our formula is un equals a r n minus 1. And we want to know when is a term greater than 1 million. Well, here we could think that is when ar to the n minus 1 is greater than 1 million. So we can replace the ar to the n minus 1 with 3 times 2 to the n minus 1. This next step, well, we can divide both sides by 3. Now, this is looking a bit like one of our logarithmic equations. So, I'm going to take logs of both sides, and again, I'll probably use base 10 here. Now, using our rules of logs, the n minus 1 can come out in front, remembering to use brackets. Next, I'm going to divide both sides by log 2. Now at this point when we're dividing, we need to think, is log 2 positive or negative? You can check on your calculator. It is indeed positive, so the inequality stays the same. So now we have log of 1 million over 3 divided by log of 2. Don't be tempted just to write log once. It's log over log. Then finally, we're going to add our 1. Now actually this comes out to be 18.35 approximately, plus our 1 means n is bigger than 19.35 approximately, which gives us, because n has to be a whole number because it is a term of the sequence, so therefore n is equal to 20. So after 20 terms, it exceeds 1 million. And you could fill this back into the original formula to check.